Discuss about inter-process communication. Okay, first, what is inter-process communication? So it's a mechanism for process to communicate and synchronize the actions, okay, which is used to communicate each other, right? Inter-process communication is used to communicate each other. Next is we need to know about the message system. This message system is a process which is used to establish the communication between sender and the receiver. Okay, message system, it's a process which is used to establish the communication between the sender and the receiver. Okay, so we have two primitives, one is send, another one is receive. Send has the fields destination and message. Another one is send. Inside the bracket, we need to mention the message. The second primitive is receive. Receive with two fields, source and message, or receive with only one field, that is message, right? Here, the message size may be fixed or variable. Message size may be fixed or variable. This diagram shows the basic message passing primitive. First, sending process contains message passing module. Uh, Same as receiving process also contains some message passing module. So here, each and every message contains a process ID. Okay, process ID. Next slide shows the message format. Here the message format consists of header and body of message. Header and body of message. In Unix, there is no ID which contains only the message type. So the message format contains message type, destination ID, source ID, message length, control information, and control contents. Similarly, the control information contains the sequence numbers and priority. Sequence numbers and priority. Okay, next is the diagram of messages and pipes. Okay, here we compare messages and pipes. So first diagram is messages. P1, P2 are the two processes. P1, P2 are the two processes. So P1 sending the message to the receiver. In between we have message queue. This message queue was fixed size messages. Okay, message queue was fixed size messages. The second diagram is pipe. So in pipe we have process 1 and process 2. Instead of send and receive, we have write and read. Okay. Here we have pipe buffer. This pipe buffer may contain fixed or variable read and write sizes. Okay. In a pipe buffer, we may have read and write in any sizes. Okay. Variable size. Next is message passing. So here, the message passing is a general method which is used for inter-process communication. So the first process inside the same computer, the second process in a networked or distributed system. Okay, network is nothing but collection of. Next, synchronization in message passing. A message passing may be in two acts. One is blocking, another one is non-blocking. Blocking is considered as synchronous, non-blocking is considered as asynchronous. So blocking send has the sender block until the message is received. Blocking send has the sender block. So sender block until the message is received. So second one is called as blocking receive, which has the receiver block until the message is available, reached. Next is non-blocking. Non-blocking is considered as asynchronous. Okay, so here the non-blocking send has the sender send the message and continue. Non-blocking receive has the receiver receive a valid message or nil. Next is synchronization in message passing. So here we have sender and receiver. First, sender can send several messages to multiple destinations, but the sender usually expects acknowledgement of message receipt. So for sender, need acknowledgement for the message receipt. Similarly, for the receiver side, it is more natural to be blocked after issuing receive. Next is IPC requirements, inter-process communication requirements. If P and Q wish to communicate, consider now there will be a communication between P and Q. Okay, P and Q wish to communicate each other. So first step to do is establish a communication link between P and Q. First step is establish a communication between P and Q. Second is now P and Q can exchange messages, okay, via send receive. Second step is once P and Q established the communication, they can exchange messages via send and receive. Next, implementation of communication link. One is physical, another one is logical. So example for physical, shared memory, hardware bus. Example for logical properties. These all are the questions while implementing a communication between P and Q. First is how are links established? Second is can a link be associated with more than two processes? The third question may be how many links can there be between every pair of communicating processes? The fourth question is what is the capacity of a link? The fifth question arises is the size of a message that the link can accommodate fixed or variable. Finally, is a link and unidirectional or bidirectional. Next, there is two communications in the IPC, inter-process communication. First is called as direct communication. Second is called as indirect communication. So in direct communication, when a specific process identifier is used for source and destination, right? For direct communication, specific process identifier can be used, okay? Second one is called as indirect communication. This indirect communication is more convenient than the direct communication, which is more convenient than the direct communication. Okay, next. So direct communication. So in direct communication, processes must name each other explicitly. Receive contains two fields. One is P, comma, messages. So send a message to this P represent P is the address. P is acting as the address. So here send a message to process P. Next is receive a message from Q. Okay, send P comma message. Send a message to process P. Receive Q comma message. Receive a process from capital Q. Okay, name of the receiver is Q, name of the sender is P. Okay, next, properties of communication link. First property is links are established automatically. Links are established automatically. Link is associated with exactly one pair of communicating processes. Also, between each pair, there exists exactly only one link in the process. The link can be unidirectional, but it is usually as bidirectional link. Next is indirect communication. Here the messages are directed and received from mailboxes. Okay, here the messages are directed and received from the mailboxes, which is also called as ports. Port. This mailboxes also called as ports. Okay, mailboxes also called as ports. Each mailbox has a unique ID. Each mailbox has a unique ID. Okay. Next, the processors can communicate it only if they share a mailbox. Okay, processors can communicate only if they share a mailbox. Next are some of the properties of communication link. So here, link established only if processors share a common mailbox. Okay. The second point about indirect communication is link can be associated with many processes. More than one process can associate it with single link. More than one process can associated with single link. Each pair of processes may share several communication links. Here, in the indirect communication, the link may be unidirectional or bidirectional. Unidirectional or bidirectional. Next, so these all are the operations and primitives of indirect communication. These all are the operations and primitives of indirect communication. So first are the operations. So the first operation is we need to create a new mailbox. Need to create a new mailbox. Second operation is once mailbox has been created, we can send and receive mailboxes through the created mailbox. After sending and receiving, destroy the mailbox. Initially create the mailbox, send and receive messages through the newly created mailbox. Final step is destroy the mailbox. Next are the primitives. Primitives are send and receive. Send a comma message, receive a comma message. So send a message to mailbox A, receive a mailbox from mailbox A. Okay. Next, inter-process communication continuation. Now consider mailbox sharing. Now process, we already discussed, many processes can share a single link, right? Similarly here, more than one processor sharing a same mailbox A. So here, three processors sharing mailbox A. The name of the three processors are P1, P2, P3. The three mailboxes names P1, P2 and P3. So P1, P2, P3 share mailbox capital A. Okay. Now consider P1 sending the messages. P1 is acting as a sender. P2, P3 are the receivers. P1 acting as a sender. P2, P3 receivers. Okay, P2 and P3 receiving the messages from P1, right? Now, who gets the message? Either P2 or P3. Either P2 or P3. Now, the possible solution for the above question is allow a link to be associated with at most two processes. Okay. Initially, allow a link to be associated with two processes. The second possible solution is allow only one process at a time to execute the receiving operation. Okay. The second solution is allow only one process at a time to execute a receive operation. Finally, allow the system to select the receiver. Now sender is notified who was the receiver was. Okay, who was the receiver. Next, mailboxes and ports. So here, mailboxes can be private to one sender, one receiver pair. Okay, now consider mailbox is a private. Okay, to send message between one sender and one receiver. Okay, look at the diagram. We have set of processes. P1, P2, P3, Pn are called as sending process. Q1, Q2, Q3, Qn are called as receiving process. Okay. Next diagram is related to the mailbox. Next diagram shows the port. Okay. The same mailbox can be shared among several senders and receivers. Okay. So mailbox is shared one. Mailbox is shared one. Here, several senders and receivers sharing a same mailbox. Okay. Look at the first diagram. Several senders, several receivers sharing a same mailbox. Port. Port is a mailbox associated with one server and multiple senders. Okay, here in the second diagram, we have more than one sender and only one receiver. More than one sender and only one receiver. Okay, so port is a mailbox associated with one receiver and multiple sender, which is used for client server application. The receiver is the server. Okay, here receiver is the server. This port is used for client server application. Okay, client is client is used to send the request to the server. Server is used to send the response to the client's request. Next, ownership of ports and mailboxes. This port is usually owned and created by the receiving processes. Port is usually owned and created by the receiving process. Port is created by receiving process. Also, the port is destroyed when the receiver terminates. Okay, the port will be automatically destroyed when the receiver terminates. Operating system creates a mailbox on behalf of a process. Okay, the mailbox is destroyed at the owner's request or when the owner terminates. See the difference between port and mailboxes. Port can be destroyed when the receiver terminates. Okay, mailbox can be destroyed when the owner terminates. Okay, or at the owner's request. Next, mutual exclusion, message passing. So now consider the first step is create a mailbox mutex, which is shared by n process. Okay. Send is non-blocking, receive blocks when mutex is empty. Now the initialization step is send within bracket mutex. It's a mailbox. Go. Okay. Look at the coding part. Process PI. VAR is a variable, that is message. Now repeat until all the messages send and receive. Okay, receive within bracket mutex comma message, then send within bracket mutex comma message. Okay, CS is sender, RS is receiver. Okay, next. Initially, the first PI is used to execute the receiver side message. PI process is used to execute the receiver side messages. Okay. All other messages will be blocked until PI resend the message. Okay. All other messages will be blocked until PI resends the messages. Next. Bounded buffer message passing. Here the producer places items in the mailbox. Okay. The name of the mailbox is may consume. Consider may consume. Now this may consume acts as buffer. Okay, buffer, which is used to store the mails. Okay, store the informations. Consumer can consume item when at least one message present in the queue. Next, mailbox. Next, using the variable name may produce is filled initially with k null messages. Initially, the value of k equivalent to buffer size. Initially, the value of k equivalent to buffer size. Now, the size of may produce shrinks with each production and grows with each consumption. So here all the solution can support multiple producers and multiple consumers, multiple producers and multiple consumers. Okay, this is the coding for the previous slide. Producer, variable P message, that is producer message, repeat until all the mails receive in the receiver part. Next, send, may, consume, comma, process message. The second half is consumer. First half is producer. Next is consumer. That is variable, consume message, message. Repeat until receive all the messages. Okay. Next. This is the producer consumer problem with message passing. Producer consumer problem with message passing. Initially, hash define n number 100. This 100 represents number of slots in the buffer. 100 represents number of slots in the buffer. So we have 100 slots in the buffer. We have 100 slots in the buffer. Next, void producer void int value, that is integer item, messages m, variable m, that is that represent message buffer. Next, which is used to generate something to put in the buffer, that is item equivalent to produce item, receive consumer comma ampersand m. This is wait for an empty to arrive. Next is build underscore message, that is address of m, construct a message to send the messages. Finally, send all the items to the consumer, that is send within bracket consumer. Okay, so this is the producer consumer problem with message passing. Next is the example of inter-process communication system. POSIX shared memory example. First, process first creates shared memory segment. Initial step is process creates shared memory segment. Okay, we need segment ID. So segment ID contains IPC private, size of the message. Next, the two variables, IR user, that is read user, write user. Okay, yes underscore read, yes underscore write. Next, process wanting access to that shared memory must attach to it. Shared memory equivalent to character, that character may be variable size. Segment ID null 0. Now the process could write to the shared memory, that is yes printf shared memory, writing to shared memory. When done, a process can detach the shared memory from its address space. So these all are the example of IPC system. The next example of IP system is Mac OS, Macintosh. So the Mac communication is messages based on system calls or the messages here. Task gets two mailboxes at creation. One is kernel, second is notify. Kernel and notify. Only three system calls needed for sending messages. First is message sent, message receive. Third one is message RPC, remote procedure call. Mailbox is needed for communication created via port allocate. Next, previously we discussed Macintosh operating system, Mac OS. Next is Windows XP OS. Okay, so here message passing centric via LPC facility only works between processors on the system, same system, which uses ports to establish and maintain communication channel. Communication works as follows. The first step is the client opens the handle to the subsystem connection port object. First, clients open a handle. Second is client sends a connection request. Second step is client needs to send the connection request. The third step is server creates two private communication ports. Third is client and server use the corresponding port handle to send messages or callbacks and to listen the replies. Next, local procedure calls in the Windows XP. So first is the client side, finally server side. Client sending the connection request to connection port. Client sending the connection request to connection port. Then connection port handle all the server request. Next, client communication port handle all the task. Next, server communication port, client communication port and server communication port. Okay. Client communication port is used to handle all the requests in the client part. Server communication port is used to handle all the requests in the server side, right? Finally, shared section object sharing both client and server. The shared section object sizes should be less than or equivalent to 256 bytes, which should be less than or equivalent to 256 bytes. Next, communications in client server system. So there are various mechanisms for establish the communication in the client server system. One is pipes, second is sockets, third is remote procedure calls. Fourth is remote method invocation, RMI. So these all are the four various mechanisms for communications in client server system. First is called as pipes, second is sockets, third is RPC, remote procedure calls, finally RMI, remote method invocation. First is pipes. The pipes or acts as a conduit. Okay, conduit is nothing but to establish the communication between two medium. Conduit is used to establish the communication between two medium. Act as a conduit allowing two processes to communicate. So some of the issues in the pipes. First is communication is unidirectional or bidirectional. In the case of two-way communication, is it half or full duplex? Must there exist a relationship? Can a pipes be used over a network? These are the issues occurred while using pipes. Next is ordinary pipes. Ordinary pipes allow communication in standard producer consumer style. Ordinary pipes allow the communication in standard producer consumer style. Ordinary pipes using producer consumer style. Producer writes to one end, right end of the pipe. Consumer reads from the other end, the read end of the pipe, the read end of the pipe. This ordinary pipes are unidirectional, right? One-way communication, unidirectional, which require parent-child relationship between communicating processes. Ordinary pipes require parent-child relationship between communicating processes. See, this diagram shows the ordinary pipes. Okay, this is the ordinary pipes. Next. So the first part is parent, the second half is child. Next are the named pipes. First we discussed about ordinary pipes. Second is named pipes. So the named pipes are more powerful than ordinary pipes. So here communication is bidirectional. In the ordinary pipes, communication is unidirectional. Here communication is bidirectional. In the ordinary pipes, communication is unidirectional. Here we don't have parent-child relationship. No parent-child relationship is necessary between the communicating process. In ordinary pipes, we need parent-child communication, child relationship. Here several processes can use the named pipe for communication. This named pipes provided on both Unix and Windows system. Named pipes are available in both Unix and Windows operating system. Okay. So the third communication is sockets. The socket is defined as an endpoint for communication. Socket is defined as an endpoint for communication. So the socket contains IP addresses and port. It's a combination of IP addresses and port. Okay, concatenation of IP addresses and port. So now consider the socket number. See here, the first four are the IP address, finally port. So IP address is 161.25.19.8 is IP address. 1625 is port number. 1625 is port number. Now the socket is a combination of IP address and port. The socket 165.25.19.8 which refers to port number 1625 on host 161.25.19.8. Okay, so socket is a combination of both IP addresses and port. Here the communication consists between a pair of sockets. Communication consists between a pair of sockets. Look at the diagram. This diagram shows the socket communication. Okay, so first is system X and web server. Now the IP address of host X is 146.86.5.20. Port number is 1625. So the port number 1625 on host 146.86.5.20. Okay. Next, the web server IP address is 161.25.19.8. Socket is port number 80 is on 161.25.19.8. Okay. Next, remote procedure calls. Remote procedure calls. So here we have stubs. So stub is nothing but client-side proxy, which is for the actual procedure existing on the server. Client-side stub. So we have stubs in. We have two stubs. One is client-side stub and server-side stub. So the client-side stub locates the server and marshals the parameters. So the server-side stub or skeleton receive the messages, unpack the marshaled parameters, and perform the procedure on the server. Okay, the same thing can be happens on the opposite direction. Same thing can be happen on the opposite direction. Okay, next. This diagram shows the remote procedure call mechanism. Diagram shows the remote procedure call mechanism. First is client application. Next is the remote server application. Client application and remote server application. So the client application contains local application or operating system. So the client application sending the local procedure calls to local application or operating system. Also client application sending the messages to local stub. Okay, that is local responses receiving from local stub to client application, local stub to client application. So the bottom of the diagram shows the remote procedure call between local stub of client application and local stub of remote server application. Next is, so this is the execution step of RPC, execution procedure of remote procedure call. First is client sending the messages to server. Okay, so see, look at the first step. User calls kernel to send remote procedure call message to procedure X. Okay, so now from addresses client to this server. See, the port name is matchmaker, address for RPCX, receiver. Okay, receiver contains the address for RPCX. So sending the message to server. Matchmaker receive messages, looks up, answer. Next, kernel places port P in user RPC message. From a server to this client, port is kernel, remote procedure call X port capital P. Okay. Now, matchmaker replies to client with port P. Next, kernel sends remote procedure call from client to server port capital P. Daemon listening to port P receives messages. So this all are the execution steps between sender and receiver. This all are the execution messages between sender and receiver. Next is RMI, remote method invocation, right? It's a Java mechanism which is similar to remote procedure call. It's a Java mechanism which is similar to remote procedure call. So here, the remote method invocation allows a Java program on one machine to invoke a method on a remote object. This RMA allows a Java program on one machine to invoke a method on a remote object. JVM is nothing but Java Virtual Machine. JVM is available on Java. JVM is a Java program. JVM is a remote object. Okay. So this remote method invocation allows a Java program on one machine to invoke a method on a remote object. Okay. Next. Marshalling parameters. See, now client server dot some method a comma b stub of client communicating with skeleton of the remote object. Okay, remote object. Okay, so these all are the points about inter-process communication IPC. Quickly, I will recall the topic. So in today's GATE class, we discussed about inter-process communication from operating system. Okay. Inter-process communication is a mechanism for process to communicate and to synchronize their actions, which contains two parameters, send and receive. Here, the message size is fixed or variable. This is this diagram shows the basic message passing primitives. First, sending process. Next, at the receiver side, we have different receiving process. Next, message format. So the message format contains message type, destination ID, source ID, message length, control information, message contents, which consist of header and body of message. In Unix operating system, there will not be an ID which contains only the message type. This is a comparison between messages and pipes. Message queue is fixed size messages, but pipe buffer is read and write in any size. Message contains send and receive operation. Pipe buffer contains write and read processes. Next, message passing. Message passing is a general method used for IPC for processes inside the same computer, for processes in a networked or a distributed system. Message passing may be in blocking or non-blocking. Blocking is considered as synchronous. Non-blocking is considered as asynchronous. Blocking contains blocking send and blocking receive. Non-blocking contains non-blocking send and non-blocking receive. So synchronization in message passing. For the sender, it is more natural not to be blocked after issuing send. It is more natural to be blocked after issuing receive. Okay, these all are about a synchronization. Next, IPC requirements. Consider the two processors wants to communicate each other. First step, they need to establish communication link between them. Then they can exchange messages via send, receive. So the implementation of communication link can be through physical or logical. The example for physical is shared memory hardware bus. Logical is logical properties. These all are the implementation questions. Next is link capacity. Zero capacity means there is no messages, empty, zero messages. Bounded capacity means finite length of n messages. Unbounded capacity means infinite length, sender never waits. Then there are two communications. One is direct communication and indirect communication. So processes must name each other explicitly. One is sent, another one is receive. Sent within bracket capital P process and message. Receive within bracket capital Q process comma message. Okay. Now the operations of indirect communication, which is used to create a new mailbox, send and receive messages through mailbox. Finally, after the communication, we can destroy a mailbox. Next, primitives are defined as send, receive. Okay. This two diagram shows the mailboxes and ports. Mailboxes can be shared among multiple senders and multiple receivers, but the port can be shared among multiple processors and single receiver. These all are the coding part of message passing mutual exclusion. Next, bounded buffer. This is the producer consumer problem with message passing. Next, we discussed three examples such as examples of IPC system, POSIX, Mac operating system, Windows XP. This diagram shows the local procedure calls in the Windows XP. Next is the communications in client server system. Four different communication mechanisms. One is pipes, another one is sockets, third one is remote procedure calls, finally remote method invocation using Java. So in pipes we have ordinary pipes and normal pipes. This is ordinary pipes. Next is named pipes. Next, sockets. So sockets is the combination of IP addresses and port. So now port number 1625 on host 161.25.19.8. This is the socket communication between host and web server. Next is RPC. RPC using steps to establish the connection between client side and server side. RPC mechanism. This diagram shows the RPC mechanism. This diagram shows the execution of RPC, remote procedure call. Next, RMI. Remote method invocation is a Java mechanism which is similar to remote procedure call. This RMI allows a Java program on one machine to invoke a method on a remote object. JVM is nothing but Java virtual machine. Java virtual machine, Java program and remote object. This is the unmarshalling parameters. Okay, so these all are the methods, processes, or an inter-process communication of operating system. Okay, so